start the recording. Okay, so we were just doing last time the digital modulation techniques, and let me very briefly review what we have done in the last class. Do the slideshow. Okay. So I think there's no need to go back to pulse amplitude modulation. So we in pulse amplitude modulation, we know that the signal points can be represented on a one-dimensional constellation diagram because we have to represent only the amplitudes, right? So this is 1D constellation diagram for pulse amplitude modulation or amplitude shift keying. So we also found out the energy of the modulated signal, and that came out to be half AM square EP, where EP is the energy of the pulse. Since AM is a variable, I mean the energy of the modulated signal will vary depending on the voltage level. Okay. And we also know now that we need to define the basis functions, because the basis functions or unit energy signals will be used to represent all the signals, all other signals, uh, to represent all other signals in the scaled version of the unit energy signal. All right. This is the modulated signal for the PAM case. The modulated signal, let's say this is the origin and this is the signal point. This will be a unit length from the origin. Now, all the other signals will be expressed in terms of the basis function. So that's the idea basically. The modulated signal is expressed in terms of the unit energy signal. All right. So this is about pulse amplitude modulation. I think we have discussed enough of pulse amplitude modulation. Let us also even we have discussed this phase shift keying. In the phase shift keying, there will not be any amplitude term. I hope you will excuse me for this sound. This will end up, I think, in a few minutes. Because outside there is some work going on. So you have to just wait for, anyway. So phase shift keying in, just give me 2 minutes, please. Let this sound end, yeah. Okay, so this is phase shift keying. Phase shift, in the phase shift keying, the just let me check till what time. Just give me 1 minute. Let me check. Okay, now it's fine. Now let me explain phase shift keying. So what is phase shift keying? This is the modulated signal, because there will not be any amplitude term, because the variable factor will be phase. So how do we represent the variations in the phase? It is 2 pi by capital M. Capital M is the number of signal points and small m is the index. The small m will vary from 0 to capital M minus 1. Right. So this is the modulated signal, and this can also be expressed in terms of the low pass equivalent signal also, because that will be the real part of this factor. Important point is that the phase in phase shift keying, the overall phase will be 2 pi. So this is the case. This diagram is the case for 8 signals. That means the complete phase of 2 pi is divided into 8 signal points. So capital M is 8. So that means 2 pi divided by 8 is pi by 4. So as we vary small m from 0 to 7, you will get the signal points, right? And this is our modulated signal. If we expand this e to the power j2 pi f naught in terms of using the Euler's formula in terms of cos and sine. We have already done all these things yesterday. And the phase shift keying can also be represented in the form of a constellation diagram using two basis functions, because phase needs two basis functions. Phase can be represented in a plane. It requires two dimensions to be represented. All right. So we will take two basis functions, phi1t and phi2t, as we took only one basis function in the case of amplitude shift keying. This is important. What is the energy of the modulated signal? So this is my x. How to calculate the energy? It is the integral going from 0 to capital T, x square, xm square t dt. So what is xm square? Xm is this function, right? If you square this and you solve it further, you will find that it is EP by 2. There is no variable factor in the energy of the modulated signal. EP is a constant because this is the energy of the pulse that we chose for transmitting ones and zeros. Initially, at a very initial stage, what the pulse we chose, so that's the energy, EP is the energy of that pulse. Therefore, this is a constant energy, PSK is a constant energy modulation. Constant energy modulation means all the signal points will be at a same distance from the origin, because the distance of any signal point from the origin is actually the representation of that how much energy is required. So since the energy is constant, so therefore all the points will find a locus as a circle. So all the points will lie on the circle, whether it is BPSK, QPSK, 8PSK, 16PSK, etc. Everything is discussed. So two basis functions are there. Phi1t we define like this, phi2t we define like this. These are two unit energy signals, and these are orthogonal to each other. So how do we prove the orthogonality of the two basis functions? It is phi1t into phi2t dt. Actually, the formula is to phi1t into phi2 star t. If we want to prove two functions to be orthogonal to each other in the time domain, then we will have to do phi1t and the conjugate of the other function should be equal to 0. So phi1t, phi2t. So what is the condition on these two basis functions? These have to be unit energy signals and they have to be orthogonal to each other. And we can express the modulated signal in terms of phi1t and phi2t. Every modulated signal, every signal in the constellation diagram, for example, it is 8PSK. For example, it is 16PSK. So 16 points are there. Every signal point can be expressed, every signal, because if it is a 16 PSK, what does that mean? We are stacking 4 bits in one symbol period. So 4 bits stacked in one symbol period. If you want to send 0, 0, 0, 0, 4 zeros, then you will have to pick this signal and you transmit through the channel with a phase difference. Here the phase difference for this signal is 0. And at the receiver, when this signal will be received, the receiver will come to know, since the phase difference is 0, so it will receive this signal and it will find out that 0, 0, 0, 0 was transmitted. And in the same way, other signals are to be transmitted corresponding to the combination of bits they are used to represent. They are used to be represented. All right. Then, so that means every signal can be expressed in terms of the basis functions with AM, BM are the AM and BM are the coordinates of the signal points. So how do you get AM? AM is given by cos of 2 pi by m, capital M into small m, root EP by 2. BM is sine 2 pi small m divided by capital M, root EP by 2. So let's take this point. The coordinates of any point in the signal constellation will be AM, BM, right? So you can find out the coordinates from these expressions. Clear? And so that's what is written here. XMT is AM, BM is a point in the plane represented by two axes defined by phi1t and phi2t. So in the constellation diagram, the one axis is phi1t, the other axis is phi2t. And every signal point is expressed in terms of these basis functions, phi1t and phi2t, as is very evident in this expression. All right. So AM comma BM is the, now let's look at this point. What is this point? This point is root TP by 2 comma 0. How do we get that? This signal corresponding to this point, small m is 0. So when small m is 0, cos 0 is 1, 1 into root EP by 2. So that means AM is root EP by 2. And for small m equal to 0, this whole factor will be 0. The coordinates will be root TP by 2 in comma 0 for this point. And similarly, we can find out the coordinates of each point using these two formulas. All right, so so XMT is so all these points actually represent the signals, but on a plane, on a two-dimensional surface, we can also put it as a vector AM comma BM also, right? AM comma BM is a point in the plane represented by two axes defined by phi1t and phi2t. All right, so this is the constellation diagram of 8PSK, and we can also choose to draw the constellation diagram for any combination of signal points, whether it is 4PSK, 8PSK, and 16PSK. The theory remains the same. Now, let's prove that we proved the energy of the signal. What do we want to prove here? We want to prove that the energy of the each signal is actually square of the distance from the origin. So that's what we want to prove. This is our modulated signal. As a vector, I can express it as AM comma BM. So what is the energy of the signal? It is integral minus infinity going to plus infinity xm square t dt. So I use XMT here, AM square phi1 square t plus BM square phi2 square t. I open the square to AM BM phi1 t phi2 t dt. Since integral of phi1t and phi2t dt is 0, because the two signals are orthogonal to each other. So this factor, the third factor is 0. The other, what are the remaining factors? AM square phi1 square t, BM square phi2 square t. But these are unit energy signals, so phi1 square t dt and phi2 square t dt should be equal to 1. So what is this equal to? AM square plus BM square. So this is AM square, energy is equal to AM square plus BM square. So what is AM square plus BM square? If you find out the distance, so what are the coordinates of origin? 0, 0. What are the coordinates of every point? AM, BM. What is the distance between the 2 points? AM square plus BM square. So that means energy is equal to the square of the magnitude of the vector, or the distance between the 2 points. AM, BM whole square is equal to, so energy is equal to the square of the distance of xm from the origin. So we can prove that the energy is actually the square of the distance. Now this is an important point. To this point needed some explanation also yesterday. So let me explain. What do we want to find out using this second point? So second point says, I want to find out the distance between the 2 points, 2 signal points. In general, I take one point as m, small m, and another point as small n. So I find out the distance between any point m and, sorry. So what do I want to do? I want to find out the distance between 2 points. And in general, one point I designate as small m, the other point I designate as small n. So in general, I say that distance between 2 points m and n, and square of the distance. Hello? Any questions? Any questions? Okay. So what is the distance between the 2 points m, m? I take one point as m, other point as n. It can be any point. It can be this point to this point, or this point to this point, right? So what is the distance? How to find out the distance between the 2 points? Use the simple coordinate geometry. Take the coordinates of this point and take the coordinates of other point and find out the distance, right? What are the coordinates of a point? The coordinates are given by these. So these are the coordinates: cos of 2 pi by m, small m, root EP by 2, sine of 2 pi by m, 2 pi small m, root sine of 2 pi by m, small m, root EP by 2. So I am taking 2 points. One point is m, the other point is n as an index. So how in place of this small m, I will use small m for one point, and I will use small n for the other point, and I will get the coordinates of a point corresponding to small m, and I can also find out the coordinates of the point corresponding to small n, and then I find out the difference. So I have here the coordinates of xm also. I have the coordinates of xn also, right? And if you find out the distance between the 2 points, I will get this formula: EP 1 minus cos of 2 pi by m. I have solved it. I will send you also. I could not put it on the slides. So, but I have solved it and I will send it to you also. So this is the distance between this important point to note here is that this is d subscript. In the subscript it is mn. It is not minimum. I will come to minimum in the next line. But what is this d subscript mn? Mn means distance between any 2 points, and that distance comes out to be ep 1 minus cos 2 pi by capital M, m small m minus n. Now, when this distance will be minimum? This distance will be minimum when the 2 points are adjacent to each other. That means the difference of m and n. What is the meaning of the difference of m and n? These are two different points. So when the 2 points are the neighbors of each other, so when these 2 points, because these are indices only, when these 2 points will be neighbors to each other, when the difference m minus n is equal to 1. That means if I'm talking about point 0 and point 1, so I want to find out the distance between the 2 points. So the distance will be minimum when the points are adjacent to each other. So when the points will be adjacent to each other, when this index difference is 1. So that means m minus n has to be equal to 1. So what is the minimum distance? That we will find out to be EP into 1 minus cos of 2 pi by capital M under root. So as m increases, I told you yesterday also, as m increases, what is the meaning of capital M increasing? That we are using more number of signal points. That means we are trying to stack more number of bits in the symbol period. But as we increase capital M, so cos 2 pi by capital M will also increase, will go towards 0. Because small capital M increasing means this argument of cos will go more towards 0. So when it goes more towards 0, this cos term will also increase. So when this term will increase, 1 minus cos term will decrease. So that means we will get the minimum distance. So what is the advantage of, what is the demerit of having distance to be as low as possible? The demerit is that if the distance between the 2 points is decreasing, that means the probability of error will increase. It will be difficult to detect different signal points at the receiver, because once the noise will affect the signals, the points, the distance between the 2 points will vary. The actual meaning is that once the noise is affecting, if the 2 points are closer to each other, it will be difficult to detect the signal points separately, right? So minimum distance reducing as capital M increasing, meaning by the probability of error will increase. I have already explained all these points um, otherwise also without explaining it through the mathematical expression. But right now here I'm deriving the mathematical expression, which clearly tells me that as capital M increases, the minimum distance between the points will decrease. That will increase, in effect, the probability of error. Okay, now let us come to another type of modulation technique, and which is quadrature amplitude modulation. quadrature amplitude modulation, right? What is the general equation of the quadrature amplitude modulation scheme? So this is the modulated signal, and this signal will be given by AM pt cos 2 pi f naught t plus BM pt sin 2 pi f naught t. Here in PSK there was no AM and BM term, right? I mean there were no amplitudes, only the phase was varying. But here in quadrature amplitude modulation, the variation can come from the amplitude also and the phase also. Let us see how. So this is the general equation of the QAM signal, modulated signal, where small m will have small m is an index. It goes from 0 to capital M minus 1, and small t will go from 0 to symbol period. Now in PSK, AM and BM were related with each other through some expression. If you remember PSK, this is my AM and BM. So this AM is having some expression and BM is also having some expression. And we know that these coordinates will result into points lying on the circle. But in the case of quadrature amplitude modulation, there is no relationship. Anywhere you can have the constellation point on the two-dimensional plane. Anywhere the point can be there. But in the case of PSK, the points will have locus only on this circle. But in the case of quadrature amplitude modulation, the points can be anywhere. It is not necessary that the points will lie on the circumference of the circle. So that means PSK will be a special case of QAM basically. Now in PSK, AM and BM were related with each other through some expression so that the points lie on the circle. But here in the case of quadrature amplitude modulation, AM and BM are selected arbitrarily. Now if this is the modulated signal, how can we express this as the low pass equivalent? It can be expressed as A plus J BM, because there are two factors are there, AM and BM. So AM plus J BM, this is the complex part of the amplitude term, and this is PT e to the power j 2 pi f naught t, and we will take the overall real part only. And this can also be expressed in the polar form. Can be also be expressed in the polar form as Vm e to the power j theta m pt e to the power j 2 pi f naught t. So from where this Vm has come? In PSK, Vm is constant. This Vm is actually equal to the magnitude of AM plus JBM. AM plus JBM is the complex amplitude part, complex expression. Now the magnitude of this complex number is Vm. The phase part is this theta m. So this AM plus JBM, which is in the rectangular coordinate, can also be expressed in the polar coordinate as Vm and e to the power j theta m. Pt e to the power j 2 pi f naught t, Pt e to the power j 2 pi f naught t remains the same. Now in PSK, this Vm is constant and only theta m varies. If you remember PSK, as I told you, the amplitude is constant, only theta m will vary. But in QAM, both Vm and theta m can vary. This Vm is actually the magnitude of this complex number AM plus JBM. So in quadrature amplitude, this Vm can also vary and theta m can also vary. But in PSK, only theta m can vary. There was no change in the Vm. So that's why the points lie on this circle. It is a constant energy modulation. But in quadrature amplitude modulation, it is not. It is not a constant energy modulation, because we can vary, we can place the signal points on anywhere on the planar surface. Now XMT is VMPT cos 2 pi f naught. So I can also express that this as VMPT if I take the real part of this, and if I take this is the complex term. So if I take the real part of the overall expression, what do I get? XMT will be equal to Vm pt cos of 2 pi f naught t plus theta m. So what is Vm? Vm is under root of am square plus bm square, which is the magnitude of this complex number am plus jbm, and theta m is tangent inverse of bm over am. That's the phase part. So QAM can be said to be joint or combined amplitude and phase modulation. What is the meaning here? In PSK, in amplitude modulation, in amplitude shift keying or pulse amplitude modulation, only the amplitude varies, the phase does not vary. In phase shift keying, only the phase varies, but amplitude does not vary. But in quadrature amplitude modulation, I can design my signal set and I can place the signals anywhere on the planar surface. So that means it is a joint combination. I can say that it is a joint combination of amplitude and phase modulation. And in quadrature amplitude modulation, it is also since it is only amplitude and phase. So how many basis functions I require at the most? I require 2 basis functions, and I will use as phi1t, phi2t, and I define my basis functions as under root 2 by ep pt cos 2 pi f naught t. Phi2t is equal to under root 2 by ep pt sin 2 pi f naught t. So 2 basis function, my modulated signal will be expressed as am phi1t plus bm phi2t as I defined in the case of phase shift keying, but only difference is that we can choose constellation points by varying Vm also. Vm is a combination, Vm is a magnitude of the complex number generated by A plus J, Am and Bm. So constellation points are decided by varying Vm also and theta m also. But in the case of phase shift keying, the constellation points were generated only by varying theta m. In the pulse amplitude modulation, the constellation points were generated by only varying the amplitude. Now, constellation diagram, let us see some some examples of constellation diagrams. So this is the constellation diagram of 8 signal points. Had it been phase shift keying, what should be the this is not the constellation diagram of phase shift keying, because the points are not, or these, there are 2 circles, one circle outer, the other is the inner circle. 4 points lie on the inner circle and 4 points lie on the outer circle. Had it been phase shift keying, all the points would have been placed on the same circle, because that was the constant energy modulation. But in the case of QAM, so I can place my signal points by varying amplitude also, Vm also, and theta m also. So if you see, if you see this point and this point, the phase is same but amplitude is different. Here so that means the point that I want to mention here is that this is an 8 QAM signal set. Had it been 8 PSK signal set, all the points would have lied on the circle, on one circle, right? So you can place anywhere in the anywhere on the 2-dimensional axis, 2-dimensional plane. So these are the constellations of 8 QAM. One example of the constellations of 8 QAM. These are the constellation diagram for 16 QAM. So I place this point, this point. This is my origin, right? So these are 16 signal points, and this is 32 QAM, in which I place 4 points here, 4 points here, 4 points here, and 4 points here. So 16 points, then 4 this side, 4 this side, 4 this side, and 4 this side. This is known as 30. These are the constellation diagrams of 32 QAM. These are known as cross. This is particularly known as cross constellation. Now let me explain once again what is the meaning of this constellation diagram. Constellation diagram means it is just the representation of signals on a diagram basis. Meaning by, I create 2 basis functions. I generate 2 basis functions. One is phi1t and the other is phi2t. What are the formulas of phi1t in the case of QAM? Let us talk. This is my phi1t and this is my phi2t, right? And I am expressing all my signals, all my modulated signal using AM phi1t plus BM phi2t. All right. So what is AM here? AM are the coordinates of this AM and BM. AM comma BM are the coordinates of this signal point. So AM and AM comma BM, if are the coordinates of this signal point, using these coordinates, I can use the unit energy signals and I can generate the modulated signal. So meaning by, for any signal point, I can generate its signal representation using this equation xmt AM phi1t plus BM phi2t. All right. So this is about QAM. I actually finished my lecture today here only. As there is a lot of noise coming, so I will finish my lecture. Varun.
Yes, sir.
Abhi lecture I will finish here only, right?
Okay, sir.
So tomorrow I will continue with. I will explain a little bit of this again, and I will continue with further modulation techniques also.
Okay, sir.
If any questions are there, you can ask. If any questions are there, please ask. चलिए ठीक है. Thank you very much.